Okay, you guys, we are going to keep moving forward with learning about acids and bases. We're going to start getting into the quantitative properties of acids and bases today. But first thing we need to do is just go through some things with the guided notes. So this is page 18 of the guide notes you can see here. And as you're getting used to, we are going to be marking off this entire page. Okay, so that's always fun. You do not have to do this page. So now let's move on to page 19. Okay, so looking up here with what would quantify an acidic solution, a basic solution, and then something that would be neutral. And there's some new, let me zoom this in a little bit. There's some new symbols and visualizations that you probably need to understand. Whenever you see this in brackets, that just refers to concentration. So we're looking at the concentration. We'll be doing it with molarity as our units. And remember, whenever we see H3O plus, that also stands for hydrogen ions. A hydrogen ion is really just a proton. There's no way it's going to hang out next to a water and not want to actually be a part of that water molecule. So there's where you see when it becomes H3O, that 3 is really just the hydrogen ion that comes from something that's acidic. So in these types of terms, an acidic solution has more hydrogen ions, and I'm just going to write it to remind you, it could also be written like this, than hydroxide ions. A basic solution is going to have more hydroxide ions than hydrogen ions, and then a neutral solution will have equal amounts of hydrogen ions and hydroxide ions. So you want to be reminded of how to understand this. And one of the takeaways you should have right now is acidic solutions will still have some hydroxide ions in it, just a very, very low amount compared to the hydrogen or hydronium ions that are there. A basic solution will still have hydronium ions in it, just a very low amount compared to the hydroxide ions that are in there. Okay? Be reminded this is scientific notation. So if we are looking for numbers that are greater than 1 times 10 to the negative 7, then a number like 1 times 10 to the negative 2 is greater, 1 times 10 to the negative 3 is greater. So anything where that exponent is a number that is a negative 6, negative 5, negative 3, negative 2, those are all greater. You're not going to be seeing things whenever we do pH like this that's anything with an exponent that is going to be a positive exponent. So whenever we talk about solutions as acidic or basic, they still are very, very small concentrations as acidic or basic whenever we talk about their pH. Okay, so these questions, we're going to be doing just these first 4 right here. Actually, I think I'll just do the first 3, and then I want you to do the bottom as part of your homework. We don't have anything like this in your practice packet, so this will give you some practice without going through the answers right away with me. So if I look at this and I see that we have our hydronium concentration equal exactly to 1 times 10 to the negative 7, I'm just trying, you don't have to memorize these, but how would we use that information to figure out, is it acidic, basic, or neutral? If it's exactly that number, this is the one time where it matches exactly to right here, so this would have to be neutral. Okay? In this particular case, we have a hydronium concentration of 3 times 10 to the negative 2. Now, if I just write this off to the side to remind you of what we're talking about here, that is the standard notation of this number in scientific. So our hydronium concentration would mimic that. What does that mean? Well, I know it's not neutral because it's not exactly times 10 to the negative 7, and it has to be 1 times 10 to the negative 7. So I got to figure out, does it match, does the hydronium number match down here? If so, then our concentration has to be less than to the negative 7. So that means like a negative 8, negative 9, negative 10. It's not that. So it must be up here. Okay, so you have to mathematically remember, pause out and remember that 3 times 10 to the negative 2 is a much larger number than 1 times 10 to the negative 7. So this case would be acidic. Okay. Again, if you struggle with scientific notation, convert it to standard. So we're still looking at hydronium here. This number in standard is a very small number. Okay, right there. And we know it's not going to be this. It's not exactly 1 times 10 to the negative 7. So it's one of these two. So is this number less than 1 times 10 to the negative 7? Or is this number going up here greater than 1 times 10 to the negative 7? Again, this is where you just need to pause and think about your mathematical skills. And you should be able to deduce that it matches this scenario. So in that particular case, we would say then that this is basic. Okay. So what I want you to do is, as part of your homework, I want you to do these 4 problems on the bottom of page 19. The answers, I think I've already actually put out on Google Classroom there. You just need to be careful because for these two, it switches to hydroxide concentrations. So pay attention using the reference. These two switch back to hydronium. Okay, so try that as practice. So we're getting into the quantitative characteristics of acids and bases. And pH is really a logarithmic scale. We've been hearing that a lot with the coronavirus when they're looking at scales, and they're talking about how sometimes it's better to identify the cases of positives and negative cases looking at a logarithmic scale. So again, think back to some of your math skills of what that means. But just some quick review when we think of things, just again for what again was scientific notation when we have things in exponents, how does that relate to a logarithmic scale? So very quickly, remember if we have something times 10 to the first, it means 10, 10 to the second equals 100. So then this is 1,000. This is 10,000. So a little bit of review. If we did the opposite, and this is where we hang out with when we talk about concentrations of acids and bases as far as pH, 0.1, negative 1 would equate to that, and times 10 to the negative 2 is 0.01, times 10 to the negative 3 is 0.001. So just some reminders with that. Remember with logarithmic scales, you can also, when we take 10 to the first, but the log of that, that is a 1. Log times 10 to the second is a 2. The log of 10 to the third is a 3. And the pattern, this is a 4. Right here is where we hang out with using this calculation we'll be learning tomorrow. So the log of 10 to the negative 1 is a negative 1. This will be a negative 2. You're basically just taking that exponent, and that's what it becomes. Okay. So our concentrations are logarithmic scales, and that kind of gets us to then what is the pH scale. Okay, and we're going to finish off with that today. Some kid must be printing something here. My printer's going. Okay, so when we think of a pH scale, in definition, it is a logarithmic scale of the, and I don't need to write out the concentration because putting it in brackets tells you that's what we're doing. So the concentration of hydrogen ions in a solution. Okay, and then this is the general field. Now you have to remember, pH, I just said, is a logarithmic scale. Here's the formula. We're going to practice using math with the formula tomorrow. But I'm taking the log of those concentrations. So if I just make something up here, let's say we have 1 times 10 to the negative 3 as a concentration for hydrogen ions. And if we were mathematically to do this, now we don't like negative numbers, right? And the whole reason this came about is scientists hate to write in scientific notations. They said, hey, why don't we take these concentrations and turn it into a logarithmic scale? And then it's numbers that we like to deal with. So if I were to take this right here and turn it into a pH, a logarithmic scale, then this becomes a 3 because, and I don't like that negative number, so I'm taking the negative of this and this becomes 3. Okay, that equates back to a pretty high concentration of hydrogen ions. So anything between 0 and 6.99 is acidic. Anything exactly at 7 is neutral, and anything from 7.01 up to 14 is basic. So tomorrow we're going to go through this example. I'll talk a little bit more about these tables and how they connect with what you're trying today. But for homework, you're going to be doing, I want you to try those practice problems there that I skipped for now. So these problems right here, go back and try those. Those answers are there. And then I believe it is questions number 25 and 26 in your acid-base packet. All of that is right there in Google Classroom. Okay, thank you very much.